I'm Kevin. I'm here to talk about IPv6 host discovery for attackers and defenders. Since we're just after lunch, everybody's probably nice and full, so this may be a sleep therapy session if I suck, but hopefully most people stay awake. Just a quick overview. First thing I can talk about is why bother with IPv6 host discovery. I'm not going to worry about the whys of IPv6 broadly, just focusing on the host discovery part. Talk a little bit about what's new about host discovery, talk a little bit about what's the same, talk about some things for defenders, so internal networks, talk about things for attackers coming in from the outside without having a real foothold, and then talk a fair amount about scanning, which is kind of one of the main methods of doing host discovery. So why do we want to do host discovery? Not necessarily about that, but I thought it was funny. So if you're a defender on your internal network, there's a good chance IPv6 is somewhere. IPv6 is, if it's enabled on interface, there's always a local IP address that's auto-configured. So IPv6 traffic can be happening even if you're not passing it out past the segment. You don't have routers doing that. So it can be active even if you haven't configured it. If you're an attacker, you're coming in from the outside. There's a decent chance IPv6 is less protected. I'll talk about a little bit about why. And it certainly pays to be aware of possible ways that you can discover information about a system that you're auditing, so on and so forth. Again, a little bit more about why. So there's at least meaningful availability. About 20% of the connections, a little over in the US, have IPv6 available to them. Maybe not all of them are using it. Certainly, a lot of the large ISPs have enabled it for cable modems. It's enabled by default on most OSs. So again, it may be running on local segments, even if you're not explicitly using it. Again, ISPs are automatically assigning v6 addresses, so if you get a router that's v6 capable, it's going to request a v6 address. Your provider's capable, it's going to give it to you. So your device may be accessible, or somebody's device may be accessible, and they may not know about it. Cloud providers are making it easier. It's kind of a checkbox depending on which cloud environment you're in. So some people are just enabling it because, oh, we can do it. And they don't have to think about it. There's a reasonable probability of somewhat lower security, so it's certainly not invisible, but a lot of the devices out there aren't necessarily perfect. They do better on IPv4, less well on IPv6. The code's somewhat less mature, so maybe a little bit of opportunity for some bugs that have been solved on v4 that people didn't think about in their v6 code. So what's new? Obviously, IPv6 addresses are 120 bits, so your sellers tells us that's 340 undecillion IP addresses. So that's a lot of IP addresses. And that's certainly one obvious thing. What's familiar? Host inventory is important, and part of host inventory is IP addresses, whether those IPs are v4 or v6. Traceroute is still Traceroute. Command name is a little different for v6. Ping is still ping, that kind of stuff. ICMP is still basically ICMP, etc. TCP, UDP. Anything that builds on top of the IP layer is still the same. It's just the IP layer, or anything that's crafting packets or dealing directly with the IP layer that needs to change. So what's new? So I talked about a little bit about the address space. IP format is new, so instead of dots between the address segments, you've got colons. Instead of 8 bits, instead of a dotted quad, you've got 16 bits per segment. So just a quick example of IP address formats. DNS record type, quad A versus single A, which kind of lines up. 128 is 4 times 32. Much larger IP address space, so if you're a business and you need IPv6 address space, your service provider is, in a lot of cases, going to give you a /48. That is 80 bits of address space that you can mess with, which is great. A lot of IP addresses, the need for NAT is substantially reduced, if not eliminated. But it's not all puppies and rainbows. /56 is fairly common as well. It gives you 72 bits. And the /64 is the generally recommended minimum allocation. So the recommendation from Aaron and Wright, the regional registries, is if you know there's only going to be a single subnet, so like a cable modem, assign a /64. Now, not all service providers are doing that, and maybe somewhat less than that. But even on a cable modem, you're going to have a fair number of IP addresses that are available. There's a new address discovery mechanism. So ARP is not part of IPv6. It's a protocol called Network Discovery Protocol, or NDP. We touched on this a little bit. There's both global and local addresses. Global addresses are routable. Local addresses are only used on the local segment. And we'll talk a little bit about that. So Defenders, nothing like a little bit of home sweet home. What's familiar? DNS, talked on that. Quad A record instead of single A. DHCP monitoring is the same. Route table monitoring. These are all common ways that you may do host discovery today. Flow collection, mostly the same. Talk a little bit about an adjustment there. All your Windows discovery commands, NVT-stat, net. Active Directory. And the list for what's the same is really too long. Most of your current host discovery mechanisms will still work. Things to adjust. Scanning, we'll talk more about that. Link local IPs, I've mentioned this a little bit. V6, your machine, if V6 is enabled, you're always going to have a V6 address, even if it's not routed. It's used for address auto assignment, neighbor discovery, some other things. Even your local router or gateway is probably not going to see most of this segment local traffic because it doesn't really need to know that you've got two machines that are talking, that need to talk to each other, and they're doing discovery between them. This can facilitate silent hosts that never talk outside the segment. So there's some normal use cases for this. Containers may be like this, in that a container is maybe only talking to applications that live on that segment. Patching doesn't happen directly to the container because you patch the host. So it may never actually need to talk outside of the segment. So that's a normal use case, but it's also a technique used by malicious or compromised hosts. So it does pay to be aware of that local segment traffic. That's becoming more important. So one of the ways to address that, expand your flow collection. So who here is familiar with the NetFlow, SFlow, that kind of stuff? A few people. So a lot of times flow collection is currently done at a layer 3 boundary. So at a router, gateway, whatever you want to call it. Because of all this local traffic and the local only IP addresses, there can be a lot of traffic that you're not going to see now. So instead of doing it at a layer 3 boundary, you're really going to want to do that at basically every single switch. So SFlow is kind of the predominant protocol for switches. That's going to become more important. You're going to be wanting to have some visibility in terms of flow to every single port, not just things that happen to flow through a router. And from a cloud provider perspective, Amazon, Google, Azure all have something, they may call it something slightly different, something flow logs, something along those lines. So a little bit about local host subnet detection. There's a multicast address that you can send an ICMP echo to. So this is kind of similar to pinging the broadcast address on IPv4. A lot of machines will respond to these right now. Windows won't respond to those. There's a modified way of doing that. It's an echo request with an unrecognized option type. you're probably going to be looking at something like Scapy or something that's not semi-custom. There may be some tools that may help you do that, but you may have to do a little bit of your own coding for that. As a way to combat undesired host detection, you may want to consider a firewall rule on hosts, which has been pretty common for local broadcasts. Pinging the broadcast can result in a local service degradation or DOS. So similar here with this multicast ping. Some more things to address. Address discovery. I mentioned NDP replaces ARP for IPv6. There's a potential for neighbor cache size issues. So IPv4, a lot of times you have what they call /24, 256 hosts there. With the expanded address space of IPv6, you can potentially have a much larger number of theoretical IPs. On Linux, if you want to look at your IPv6 neighbor list, there's a slightly different command. It's IP-6 neighbor show. An NDPmon, if you want to use a tool that can kind of look at what's going on. That's a neat tool to kind of get an idea of what's actually going on at a packet level and a message level with NDP. And NDP is done by Element. So a little bit of information that's kind of attacker specific. As an attacker, if you've upgraded your gear, maybe your client or whoever it is has maybe not updated theirs. So some IPv6 awareness can be a tactical advantage. Again, a few things that still work from a attacker perspective. And DNS, finding stuff via DNS works. Search engines, Showdown's actually got IPv6 support. Typical Google stuff. Application analysis, looking at what an application is doing, both at a code level and a network packet level. Again, Traceroute pings. Route analysis, so BGP looking glasses, that kind of host or at least subnet level discovery if you're doing reconnaissance. Whois tells you a lot of information about IP allocations, what IP ranges are assigned to what organizations. If they're child allocations, tell you what the upstream allocations come from. And then, again, that's kind of a quick list. There's a whole lot of things that still work. Generally, most things above the IP layer that you're using for sources of information today will still work. Some things to adjust. Scanning. So that's a common thread for both attackers and defenders. Some of the considerations for scanning are going to need to get adjusted. Research and reconnaissance. From an external perspective, if you don't have you may have authorization to scan the network, but you don't necessarily have a foothold inside the network. Research and reconnaissance becomes more important because of the broader IP space. It can become a lot more difficult to find hosts just by brute force. And then finding ways to use the data from your reconnaissance quickly and effectively to improve your scanning and discovery processes. So scanning. Keeping scanning manageable. So the broad address space and your /64, so 64 bits of address space, you're probably not going to scan that brute force, so you're going to need to bring data from other sources. I mentioned several already. Many others exist. A lot of the current stuff, if you're doing extensive reconnaissance and analysis as part of an audit or an engagement, a lot of that stuff still works. That information, I think, is becoming more important. A good V4 scan is also remains important. So just because V6 is available, it might be fun to play with. Having a good V4 scan will help inform your V6 scan. A lot of times the subnet boundaries are going to line up. Addresses obviously are going to be different, but knowing what those subnet boundaries are is important. And there's some some shortcuts that people may use for addressing. We'll cover here in a little bit that may help. Also, UPnP, SSDP against v4 can also expose v6 addresses that are actually in use. So you don't even have to discover them. If somebody's got a device that's using UPnP or SSDP, that would definitely be something to try. So neighbor cache size issues. I mentioned this briefly. So if the /64 is the smallest subnet that gets assigned, and that's to the 64 potential neighbor mappings, obviously no host can hold that many potential neighbor mappings. So if that table fills up, there's a potential for false negatives, so you could have a host that's up and good, but your scan misses it because that neighbor discovery table is full. So that has some implications for scan rate. There's some extra incentive to parallelize your scan, understand your network, scan multiple subnets simultaneously. There is a potential for a denial of service. The device probably isn't going to go down, but other devices on that network may not be able to get their entries into that neighbor table, so they may not be able to get outside their segment for some period of time. Obviously, if you're an internal person trying to scan your network, trying to understand your host inventory, you don't want to DOS yourself. If you're coming from the outside, probably don't want to cause a denial of service. That's an indication that something might be happening. If packets stop flowing, generally not going to make for a happy client unless it's a kind of a specific type of exercise. A little bit more on neighbor cache size issues. There's a fair amount here. I'm going to go through this a little quick just in the interest of time. Incomplete neighbor discovery entries are generally held for 3 seconds. So just running a quick calculation. If there's a 512 entry limit, that generally means you can scan probably about 170 unique IPs per second on that segment without busting that neighbor discovery cache. If the timeout is longer, just over 5 seconds, it's about 100. You can do the math to kind of break that down. But again, controlling your scan rate becomes a little important. Some knowledge of network topology, so I talked a little bit about parallelizing on different So that knowledge and parallelizing your scans is becoming more important for IPv6. There's some potential that admins may reduce their subnet sizes, again, to reduce the risk of busting the neighbor discovery table, which could actually make scanning a little easier. So that is something to keep an eye out for. There's some benefits to that for an admin. But there's also benefits to having a broad address pool with hosts that are hard to find. So gaining a foothold. So especially from that outside, when you start to scan, you don't necessarily know a huge amount about the network. But there's some initial techniques that you can use to start to get a foothold. So some IPs are going to be configured with an ease of use in mind. Your routers, your DNS servers, NTV servers, common fundamental infrastructure along those lines are probably going to use IPs that are fairly easy for the administrators to remember and configure. A lot of those assignments only use the last byte, sometimes the last 2 bytes. So that gives you 2 to the 8th hosts, very easy to scan 2 to the 8th hosts, 256, or 2 to 16, 65,000 hosts. Again, both very easy to scan. Quick examples of common router gateways for IPv6. So instead of .1:1:254, or now since F is the last hex number, that is becoming a common IP for routers and gateways. And then you've got single F up to quad F, depending on how the admin was feeling with that. Some IPs may embed a port number, so people may assign :53 to their DNS server. Easy to remember. Again, if people are doing this, if you're only checking 1024 and below, 2 to the 10, that's 1,000 hosts. Again, 2 to the 16, 65,000 ports, 65,000 hosts. Again, not very difficult to scan that in a reasonable amount of time. Because IPv6 uses hex, hex speak, aka wordy patterns, are not possible. An example of badass. Anybody gets the cow reference in the corner? We can talk about that later. But it essentially allows the use of mnemonic devices to enhance ease of use. If you want some examples of some hex strings, there's a good Wikipedia article, a whole bunch of stuff. If you've done any embedded firmware development, these are common in that area. V4 info it can be embedded, so they can. A few quick examples. You can take an IPv6 prefix and then just put your IPv4 addresses at the end of it. This is a quick example of breaking out a 172.16 network into so you have a prefix that's this 2001 DB8, and then this is the equivalent 172.16.1.0/24, and that's kind of repeated twice as both the subnet and the IP address. So if they're doing that, then that may reduce their effective IPv6 footprint to the same as their IPv4 footprint. So if they have a /24, well, that's a lot fewer addresses to scan. /16 is a really big IPv4 subnet, but still a manageable address set to scan. Strategic randomization. So one way to try to cover as much area as possible, if you have a large address space, you can say, okay, how many IP addresses can I scan in the amount of time that I have? So I threw together a quick example. If you can scan 1 million IPs in 24 hours, you got 5 days to complete a scan. That's 5 million IPs. So you can compete n number of random hosts. So you could compute n number of IP addresses within a /48, so 2 to the 80, or within a /64, and just start scanning those. Obviously, not everything is going to find, but there's some people from the Center for Advanced Internet Data Analysis. They actually found that they found somewhere between 50 and 30% of the hosts that were up in using this technique. So as far as gaining a foothold, this is a good way to go. You can also do similar things at a subnet level, so you can break it up into subnets and hosts, and then figure out how many subnets you can do and then how many hosts per subnet. Branching out. So once you've got a foothold, obviously you're probably not going to have a full picture with IPv6. So you use your discovered host as a seed. So we know these hosts exist, and then you expand out. A simple mechanism for that would be just expanding by some plus-minus range. So for every IP that you know is good, you scan ±10 hosts, ±100 IPs. Again, informed based on what your scan capacity is, how quickly you can scan, what the time period is. Using sequence completion. So if you do a trace route, you're going to have different hops along the way. So this is a quick example of a hop, a couple hops where you have BAAD:1 is a hop, and then BAB1 is another hop. Well, between BAAD and BAB1, you've got these 4 hex addresses. So you can say, well, we know they use this, we know they use that. There's a pretty good chance that there's some addresses in the middle that are also used. So you can flag those as subnets to scan more deeply, or hosts to look for a little bit more explicitly. Continuing to branch out. So auto assignment schemes. IPv6 has a built-in IP address auto assignment. The default mechanism is stateless auto address configuration. which is essentially using embedded IEEE IDs. We often think of them as MAC addresses, which is generally often true. There's a little bit more behind it, but we don't need to get into those details. The default is to take to build 64 bits of address space. First 24 are based on the OUI, which is the MAC assignment that was made to the vendor. The next 16 bits are fixed in the FFFE pattern. And then the next 24 bits are the low 24 bits of the MAC address, so the least significant bits of the MAC address. So if you have a subnet, you know this is a good subnet, you know they're using IEEE IDs, and you know, well, they've got a whole bunch of machines from a certain vendor, you know what that vendor's OUI is, then that gives you 2 to the 24 hosts at most, maybe 2 to the 23rd, depending on some technical issues. And if you want to know what the OUI assignments are, IEEE has all of those published because those are all paid allocations or most of them are paid to IEEE. Often the lower 24 bits are not random. Machines are bought in batches, deployed geographically, etc. Although as machines age out, break, get replaced, that correlation does reduce somewhat over time. Virtualization. So just like with physical hardware, there are MAC addresses that are assigned to virtual systems. VMware has a few patterns. In particular, if there's an automatic MAC assignment from ESX, it's getting probably a little long in the tooth now, and you happen to know the IP of that ESX server, you can reduce your scan for virtual machines on that host to 2 to the 8th, so 256 potential hosts on that particular VM host. There's MAC address, manual MAC assignments, again, a slightly different OUI, and then a reduced range of the last 24 bits for some compatibility reasons with VMware. Don't need to go through all of these. Docker has a base of 02 home 42 plus the v4 address. Admins can override that and assign them manually, but then Docker doesn't do a duplicate MAC check for manually configured MACs. So most of the time, you're looking at a 2 to the 32 number of IPs to scan with Docker. And that applies to Kubernetes, obviously, as well. There are privacy extensions for IPv6 Slack. Those are becoming more and more common. This will become less useful over time, but for now, it's something worth keeping in mind in terms of informing your scans and being more effective. DHCP, anybody that's using DHCP, admin's probably going to choose a narrower range of IPs for DHCP. Some servers still assign them sequentially, so that can be a benefit. Okay, takeaways. So expanded IPv6 address space has some opportunities for both defenders. It's a little easier to hide. Also for attackers, full visibility of IPv6 probably isn't there. Some human and technical factors that mean v6 addresses often aren't random. Some knowledge of the network topology it becomes more important for reasonable host discovery with v6. Research and reconnaissance also becomes more important. And the ability to combine data from multiple tools. So combining the data from your research and your reconnaissance, from your knowledge of network topology becomes more important. However, developing these capabilities also will benefit other capabilities within the organization. So I think we gave the assignments all done. And any questions? That was a fair amount. We answered pretty quick. Okay. Yeah.
I think that DDoS application attacks are similar for how it exists with IPv6 because you can't scan for IPs.
So the question was, do you think that DDoS attacks over IPv6 are going to go away? because of the reduced ability to scan at high rates. I suspect probably not. And all you need is one good scan to know what hosts are there. And to some extent, all you need to know is what the router's IP is, so you can find that via traceroute. So if you can swamp their circuit, then the DDoS is still effective, even if it's not necessarily targeting a single host. There may be some change, although the larger address space also means larger packets. So your amplification factor may have a small bump to it. Yeah.
Are those reserved ranges we talked about that documents are using, are those actually reserved somewhere, or do they just swap them and run the rest of the future collision?
So the IP ranges I used here are actually reserved ranges for documentation for examples, but yeah. Okay, thank you very much.